Now we are looking at the influence of electric fields in matter. Okay, matter, solids, liquids, gases, metals, etc., can be classified into two: conductors and insulators. Insulators are also called dielectrics. So matter can be broadly classified into two: conductors and insulators. Insulators also called dielectrics. So what are conductors? Conductors are substances that contain an unlimited supply of charges that are free to move throughout the material. Okay, so conductors contain huge amount of charges that are free to move through the material. Metals are excellent examples for conductors, and we know in a typical metal, 1 or 2 electrons per atom are free. They are not tightly bound to the nucleus, and they can freely roam around at will throughout the material, throughout the metal. So it has a huge amount of supply of electrons, the charges which are free to move throughout the metal. So it is a conductor. Okay. Then the insulators. In the case of insulators, all charges are attached to the specific atoms or molecules. They are very tightly bound to their respective nucleus, and when they can move only very slightly, little bit within the atom or molecule. While in a conductor, the charges are very free. They are free to move at will throughout the material. In insulators or dielectrics, the charges are attached, very tightly attached to the specific atoms or molecules, and they can move only slightly. They can move very slightly within the atom or the molecule. And there are two principal mechanisms by which the electric field can change or distort the charge distribution in atoms or molecules of dielectric. Okay, so if you apply an electric field to the dielectric, to the insulator, or if the dielectric or insulator is placed in an electric field, there are two mechanisms by which electric field can change the charge distribution, can distort the charge distribution in their atoms or molecules. The mechanisms are stretching or rotating. Stretching or rotating. Okay, so in the next section, we will see how the electric field can stretch the atoms of a dielectric, inducing dipole moment. Okay, so we see the inducing of dipoles or dipole moments in an atom when it is placed in an electric field. Okay, so let's look what happens when a neutral atom is placed in an electric field. What we have shown here is an atom at the center of the atom there is a positively charged core, the nucleus. Okay, at the center you see the nucleus, positively charged one, and an electron cloud. Okay, an electron cloud surrounding it, a negatively charged electron cloud surrounding it. So this is how an atom is. The center portion, a positively charged core, the nucleus, and a negatively charged electron cloud surrounding it. And when the electric field is zero, when there is no electric field, the core, the positively charged nucleus, and the center of the negatively charged electron cloud both coincide. Okay, both will be coinciding. Now, if it is placed in an electric field, see, the electric field is not equal to zero now. Okay, electric field greater than zero. Then what happens is the nucleus is pushed in the direction of the field. Okay, the nucleus is pushed in the direction of the field, and the electron cloud, negatively charged one, that will be pushed in the opposite direction. So as shown here, the center of the core, the nucleus, that is positively charged, it will be pushed in the direction of the field. The field is from left to right. Okay, the field is from left to right. So the nucleus will be pushed in the same direction, while the electron cloud surrounding it will be pushed in the opposite direction. Then if the field is not that strong, small fields, if you are considering small fields, an equilibrium will be soon established. Okay. For the positive and negative charges, negatively charged cloud pushed in one direction, positively charged nucleus pushed in one direction, they will be attracting each other. Okay. So an equilibrium will be established for the positive and negative charges. They attract one another, and that attractive force exactly balances the force by the external electric field. The force by the external electric field on the positive and negative charges, that will be balanced by the force of attraction between the positive and negative charges. Okay, so an equilibrium will be soon established. Okay. So two opposing forces are there. The external electric field pulling the electrons and nucleus apart. Okay, that is one force. The second one, the mutual attraction between the electrons, the electron cloud and the nucleus, the attraction drawing them together. Okay, drawing them together. So they reach a balance. Leaving the atom polarized. Okay, important point. Okay, so the atom is now polarized with positive charge. The nucleus shifted in one way, and the minus, the negative charge, pushed in the other way. Okay, so in equilibrium, when the two opposing forces are in are balancing each other. The situation is this: electric field applied in one direction from left to right, the positively charged nucleus pushed in that direction, and the negatively charged electron cloud pushed in the opposite direction. Okay, and there will be, a dipole moment. Now we see a positive charge, a negative charge here, separated by a small distance. So that induces a dipole moment in the atom. So there will be a dipole moment. Okay, so the atom now has a tiny dipole moment. Okay, the atom now has a tiny dipole moment which points in the same direction as that of the electric field. Okay, see the dipole moment, it's a vector, it's pointing from the negative charge to positive charge. So it is pointing in the same direction as that of the electric field. Okay, now typically, if the field is not that strong, if it is weak, the induced dipole moment is approximately proportional to the field. The induced dipole moment is approximately proportional to the field. Okay, so P is equal to alpha E. The dipole moment P is equal to alpha E, where alpha is the atomic polarizability. Okay, which is the proportionality constant. Alpha is the proportionality constant, which is the atomic, which is called the atomic polarizability. Okay, so for weak fields, the induced dipole moment, the dipole moment induced by the field, is proportional to the field, and that proportionality constant is alpha, which is called the atomic polarizability. The value of alpha depends on the structure of that. It will be different for the different atoms. For hydrogen it is 0.667, for helium 0.205, lithium 24.3, for beryllium it is 5.60. Okay, all of these are written in units of 10 raised to minus 30 meter cube. 10 raised to minus 30 meter cube. Here what we have taken is alpha by 4 pi epsilon 0. So these are all not alpha, but actually alpha by 4 pi epsilon 0 in units of 10 raised to minus 30 meter cube. Okay.